Hi, welcome to this video. My name is Marie and together with Masoomeh, we will introduce you the concept of knowledge transfer in medical imaging. So we will first introduce you with the theory behind, and then you will be able to experiment a bit with some small examples we have prepared. In this tutorial, we will first introduce you the well-known concept of transfer learning, and then in the second part, we will introduce you knowledge distillation. So let's start with transfer learning. So what is transfer learning? You can think of transfer learning as transferring some knowledge you already acquired from a source task to a target task. Maybe let's have a look at more concrete examples. For example, if you know how to hike, it would be easier to learn how to ski. If you know how to solve puzzles, you shouldn't be too scared to learn how to play chess. And as a final example here, if you ever learned as a child how to bike, it should be easier to learn how to drive a car as you will already have some notion of road rules, for example. The next question is, why do we want to use transfer learning? So let's compare traditional machine learning with transfer learning. Here we will see four main reasons. The first reason is the size of your data. You need less data compared to traditional machine learning. The second reason is time. It will be much faster to train your model as you don't start from zero, but you start with some previously acquired knowledge. The next reason is performance. Your models that use transfer learning should reach a better performance. And finally, this goes with the previous reasons, but it will help to understand why. Let's see the initialization of your model. In traditional machine learning, when you look at the initialization of your features, you're starting your learning from zero. So here, as an example, it basically looks like random noise. But with transfer learning, you will start from already learned concepts. So if your source model was to learn to recognize the human face, you will have different level of features. So low-level features are there to recognize edges, curves, dots, and so on. And then you will have middle-level features, which will be part of the face. Here we can see an eye, a nose, a mouth. And finally, there will be high-level features, and we can see here really part of the entire face. Maybe, as you can imagine here, for any other image detection tasks, the low-level features should be more or less generalizable. When do we want to use transfer learning? So this goes a bit with the previous slide of why using transfer learning. So we will think of using it when we have a low amount of data in the target task, but a large amount of data in the source task. Another reason is when our source data and target data are similar. So where to use transfer learning? We will see here two examples, and I will rapidly refresh the two concepts if you're not very familiar with them. The first one is classification. For example, we get some pictures of cats and dogs, and we want the model to tell us for each picture whether it's a cat or a dog. It's really as simple as that. The second example is segmentation. If we have four people holding their hands together, we want the model to learn to draw the contour of each of these four persons by recognizing what is one single person. Now let's see how to use transfer learning. So there are three different strategies we will see here. And for all of them, we are taking a model that was trained on the input source. We remove the output layer that will do the prediction because we will have another task for our target input. And we replace it with a new classifier. And then we can either retrain the entire model, train some of the layers and leave the others frozen, or freeze the convolutional base and only train the classifier layer. Now let's have a look at the two examples we have prepared. So the first example, as mentioned before, is a classification task. Our source task here is a model that was trained on ImageNet. So ImageNet, if you don't know, is a large dataset with more than 1 million natural images. And these images are dogs, cats, cars, boats, houses, and so on. And it's quite impressive because this dataset has 1,000 classes, so very big. Here as an example, if you give an image of a leopard, so the model is supposed to have learned what is a leopard, and he might tell you he's 90% confident it is a leopard, but he thinks it might also be a cat. Once the model is trained, we will take all the features that were learned to classify these 1,000 classes, and we retrain the model for our new task. So in this example, we want to classify some histological H&E tissues into 9 different tissue types. For example, here we have an image of lymphocytes, and the model, after being retrained, is 80% confident that it is lymphocytes. But it also sees some notion of debris in the image. Now I invite you either to pause the video and take a bit of time to run the tutorial on the histology images, or you can just open the link and take some time later. So the tutorial here is a Jupyter notebook written in TensorFlow, and it's on GitHub. So here you will really get each step explained in a very detailed way, and you will get to better understand the concepts we just saw. Now I will let Masoomeh explain you an example on segmentation task, and she will continue with the theory on knowledge distillation. I really hope you're gonna have a lot of fun. Bye.
Hello, my name is Masoomeh, and in this video I'll be talking about the concept of knowledge distillation. But first, let's wrap up the topic of transfer learning with an example of transfer learning in medical image segmentation. Similar to the classification task, we can train a segmentation model by the knowledge learned from the natural images. In this case, our source task is a model which was trained on ImageNet, as Marie already explained to us, and the target task is a prostate segmentation. In this example, an encoder-decoder architecture is used for both tasks. Once the classification model is trained on the natural images, the weights learned by the encoder part of the classification model will be used to initialize the encoder part of the segmentation model. Then, the decoder part will be trained by the images from the target dataset. So, as you can see in this example, the concept of transfer learning can be also used to transfer the knowledge between different tasks. Now, let's have a look at the concept of knowledge distillation. Most of the best performing algorithms in different applications of classification and segmentation belong to the deep learning models with large number of parameters, which takes long time to be optimized. The privilege of training a cumbersome model is that they can easily extract the structure from the data. They are so powerful, but their main drawback is computational complexity and substantially large inference time, which makes them impractical to use in real-life applications. And this is where knowledge distillation can help. What is knowledge distillation? The idea behind the knowledge distillation is to use the knowledge learned by the best performing model, which we call it teacher model, to teach a new, simpler model with less parameters, which we call it student model. With this analogy, the concept of knowledge distillation is implemented in the setting of teacher-student framework, where the higher capacity of the teacher model is used to train a student model with less parameters and faster inference time. But let's see what's the main difference between the transfer learning that we already introduced with knowledge distillation. In the transfer learning, we usually work with the same model architectures for both models, and we copy the weights of one model to the other. Whereas in knowledge distillation, a student model can have a different architecture from the teacher model. On the other hand, in knowledge distillation, what a student model tends to imitate is the output of the teacher model. The main question is that how knowledge distillation works. To get a better insight on how this framework works, let's compare the training setting during the knowledge distillation with a normal supervised classification. For a normal supervised classification, the way that we train a model is to minimize the objective function that connect each data point with a label, which we call it one-hot encoded. This way, the labels are associated with the data point by 100% confidence, and we force our model parameters to learn them confidently. However, there might be some data points which are very similar, like the similarity between cat and tiger, and it would be helpful if we show this similarity to the model by saying that the input image is a tiger by 90% chance, and there's a good chance of 10% that it is a cat. So that's how knowledge distillation works as a regularization method which benefits from the prediction power of teacher model. Where to use knowledge distillation? You can find several applications of knowledge distillation in the literature review. One of its main applications is model compression, in which a compact model is trained under the supervision of a larger pre-trained model or an ensemble of models. So in this context, both models of teacher and student are trained based on the same input. However, knowledge distillation can be also used in the context of domain adaptation or cross-model distillation. In this case, the teacher and the student model works on different data domains, and it's hypothesized that the representation learned by the teacher model contains valuable information which can refine the training of the student model. If you want to learn more about the topic of knowledge distillation and how you can implement it, there's a tutorial on my GitHub page in which I have explained all the required steps to implement a knowledge distillation framework. Here you can find the link to this tutorial. To sum up, in this video, we introduced two main concepts of transferring knowledge, including transfer learning and knowledge distillation. We briefly explain each concept and provide you with some examples in the field of medical imaging, such as classification and segmentation. I hope you enjoyed the video. To learn more about our project, please visit our website hybrid2020.eu. Thank you.